Okay, so maybe let's start the talk. So welcome to the first talk this morning. It's our great honor to have Professor Bjorn Poonen from MIT who will talk about the heuristics for the arithmetic of elliptic curves and abelian varieties. So let's welcome.
Okay. Okay. Thank you very much for the invitation. I'm very sorry that I wasn't able to be there in person. I'm at some other. I'm organizing some. Well, I was organizing some conferences here in at MIT. Anyway, so okay, so I'm going to talk about some joint work that I've done with many people over the last 10 to 15 years, and over this time, there's a coherent picture of the arithmetic, at least conjectural picture of what the arithmetic of elliptic curves looks like. And it's been, yeah. And so this is what I want to explain. And I'll also explain some newer things that have some consequences of this picture that have come out since then from other people's work. Okay, so let me start by just reminding you of some old theorems. So if you use an elliptic curve over Q, then Mordell proved that the group of rational points E of Q is finely generated, and so therefore it has this structure. It's Z to the R direct sum some finite abelian group, and we know everything about the torsion subgroup, about this finite abelian group. Mazur worked out all the possibilities in a famous theorem, and so the mysterious part is the rank, and already in 1901, Poincaré was asking what the possibilities were for the rank. And so in particular, you can ask whether the rank is bounded as you vary the elliptic curve over all elliptic curves over Q. And it seems that the consensus about this seems to have shifted several times over the years. So originally back in 1950, it seemed that people seemed to think the answer was yes, and then for a while people thought the answer was no. Maybe it's Castle's fault. I don't know. Anyway, it looks like he started with the nose. So okay, and there are some good reasons for thinking no as well, because over this period, it was proved that in the function field analog, then the answer really was no. And also during the 1980s and 1990s, it seemed as if every 2 years or every couple of years or so, somebody would find an elliptic curve of higher and higher rank. But that stopped in 2006. The record from 2006 hasn't changed since then. And also, okay, and recently there have been several heuristics predicting that rank should be bounded. And yeah, so I'm going to talk about one that's different from those. And one of the features of the heuristic I'm going to explain is that it not only does it model the ranks of elliptic curves, but it simultaneously makes predictions about Selmer groups and Shafarevich-Tate groups. And some of these other, and they're all these conjectures are all interconnected. And some of the pieces of this collection of conjectures can be actually checked, and there are some theorems that corroborate some aspects of this. And so that's what gives me hope that this heuristic is correct. And yeah, and one of the outcomes of this heuristic is that the rank is a most 21, except with finally many exceptions. In fact, there are exceptions because we know there are some elliptic curves of rank greater than 21. By the way, Granville and Watkins, Watkins was sort of an extension of Granville's heuristic. And that heuristic also suggested that 21 should be the bound beyond which you'd only have finally many. So I don't know if that's a coincidence or if it's the truth. By the way, although this heuristic is predicting this 21, it wouldn't surprise me too much. This is sort of assuming that things are more or less random and they're not too there. But if they are special, it's possible that there could be special families in which you could have more higher rank, but things would have to be very wrong in order for the rank to be unbounded. I mean, the situation I imagine it as being similar to what happens in Maning's conjectures about counting points of bounding height. That those conjectures, I mean, they only apply if you exclude certain subvarieties, and it could be that there's a similar situation here. Okay, so let me now really get started. So, okay, so elliptic curve, as you probably know, is over Q has this kind of equation, and if over Q you can always change variables to make it so that A and B, you can clear denominators to make it so that A and B are integers, and you can make the equation. You can choose a unique representative in the isomorphism class if you put this additional condition that there's no prime that such a p to the fourth divides A and p to the sixth divides B. I mean, if you had such a prime, you could scale x and y to eliminate that p to the fourth and p to the sixth. Okay, so I'm going to look at elliptic curves in that form. So, and then this curly E will be the set of all such elliptic curves. So I have one from each isomorphism class. And when I talk about all but finally many elliptic curves, I really mean all but finally many elements of that set. And for an elliptic curve in this form, we can define some kind of naive height of that curve, and just in terms of the size of the coefficients. So, I mean, A and B are integers, so you can take the absolute value of these particular expressions, and that, yeah, okay. And the reason for introducing the height is because I want to talk about what happens statistically, but they're infinitely many, so I can't say, if I want to say something happens 50% of the time, I mean, that'll depend on how I order what I can say is if I order them by height, then you could say, well, as the height bound goes to infinity, then the fraction of elliptic curves satisfying a certain condition could be 50%. Okay, so all right, so and because I'm going to be computing averages over all the elliptic curves, I'll want to know. Well, I want to know what the denominator of the average is. So I want to know the size of how this grows as the height bound grows. And that's quite easy because to bound the height is the same as if you say the height is less than or equal to h, you're basically saying A is something up to about h to the 1/3 and B is roughly up to a constant, it's h to the 1/2. So multiply those together and you get how many elliptic curves there are up to, yeah. So h to the 5/6. Times some constant, but I'm going to be ignoring constants because they're going to be, yeah. Okay, so I also want to introduce the notion of Selmer group. So this comes from, so the Selmer groups are used to get an upper bound on the ranks of elliptic curves. And okay, so let me go through the construction. So you start with this exact sequence, given where here you have the multiplication by n map, and its kernel is here, and over Q bar, the multiplication by n map is surjective, so you get this exact sequence of Galois modules. And if you take Galois cohomology, then you get H0, you get the E of Q mapping to E of Q via multiplication by n, and then the next term is H1 of this, which is here. And if you want, you can contract this long exact sequence on the left by replacing the group here by the co-kernel, which is this. Okay, and so this, yeah, and this tells, if you know so this what this is, and you also know the torsion subgroup of B, then this will tell you what the rank is. So this is sort of the goal as far as the rank is concerned, figure out what this group is. And what this Galois cohomology tells you is that this injects into this cohomology group. But unfortunately, this group is always infinite. And so this is not very useful as an upper bound as it stands. And so what do we need to do is to figure out bounds on what the image of this in here is. And it's too hard to figure out directly what the image is. So what we'll do instead is we'll work locally. So instead of working over Q, we'll write down the same sequence over QP, the field of p-adic numbers. And you again have this injection, but now these groups are now finite, and you can actually calculate these. And so this is easier. This bottom row is easier, and you can do this not just for one prime, but you can do this for all primes. You can take the direct product, and you'll get a commutative diagram like this. And what we're going to do is observe that if you have something that's in the image of this map, so you have some element here that's in the image of the global map, then just by the commutativity of this diagram, if you map that element down here, then this element down here must be in the image of the local map too. And that gives a constraint on which elements here can't have a chance of coming from E of Q, from E of Q mod N E of Q. Because, yeah, so that defines a condition, and that cuts out a certain subgroup of this cohomology group. The ones that are the elements here that are sort of locally, they're locally in the image. And so that's the definition of the Selmer group. So yeah, so let me give this, so this let me call this map beta here. And then the Selmer group is a subgroup of this group. It consists of the cohomology classes whose image down here under beta is in the image of the local map here. And just by the commutativity, this group is an upper bound for this group, which is the one we want to know. But the advantage of this group over the whole group here is that this group turns out to be finite, and also it's also computable. And so we'd like to understand, and in fact, this is really the only way to get upper bounds to get provable upper bounds on the rank of an elliptic curve that we know of. So yeah, okay, so you have this group given any n greater than 2 and any elliptic curve. So that's just, yeah. Okay. Now from the same Galois cohomology that was on the previous slide, if you look at a couple more terms in the long exact sequence, you can extract from it this short exact sequence that measures the amount by which the Selmer group overshoots the group you're trying to measure. So the error in between what we want to know and what we can compute is this group, which is the n torsion of the Chaffray-Shape group. So okay, I'm not going to define the Chaffray-Shape group. I mean, it's not too hard to define, but the definition. I'm not going to actually use the definition in my talk. So okay, so you have this sequence, and you can also vary n in this. You have one exact sequence like this for each n greater than or equal to 2, and in particular, if you let n run through prime powers of a particular prime, and you can take a direct limit, and you'll get what's called the P the infinity Selmer group. It's no longer a finite group, but it's a group. It's a ZP module of cofinite type, meaning that concretely that means it's a power of QP mod ZP, a directed sum with some finite P abelian P group. Yeah, and the number of copies of QP mod ZP should be the rank of E of Q because of this sequence. Because this group here is conjectured to be finite, and if that's true, then the number of copies of QP mod ZP here should be the same as here. Okay, so and what we're going to do is in order to model the rank, we're not just going to look at the rank in isolation. We're going to try to model this entire sequence here, this entire exact sequence of ZP modules. So okay, so I can now let me tell you what the model is. So okay, so I'm going to work my way up to it. So first, I'm going to describe the model for the P Selmer group. So the P Selmer group is just is a fine dimensional FP vector space, and so the question is, how do you get a random fine dimensional FP vector space? And there are lots of different ways, so I'm going to show you one way, and the reason that we think that this way of generating a random fine dimensional vector space is the right one is that it's consistent with some theorems that have been proved by Heath Brown and Swearingen Dyer and Daniel Kane. So in fact, that's why that was how we came up with this. That's how we came up with this model for this linear algebra construction of a probability distribution. We just tried all the ways we could think of generating a random fine dimensional FP vector space and looked at what distributions we got, and we found that one of them exactly matched what Heath Brown had proved in 1994. And so based on that, we conjecture that that's really that's true what it should be. Okay, so what is the model? So, okay, so you start with an even dimensional FP vector space equipped with the hyperbolic quadratic form. So this particular quadratic form. And then a subspace, an FP subspace of this 2n dimensional space that is called maximal isotropic. If first of all the quadratic form is 0 on that subspace, and also it's equal to its own to its perpendicular subspace. So this in particular forces the z to be half the dimension. So z is going to be n dimensional. And so, well, I mean, so this is all happening in FP to the n, to the 2n. So there are only finitely many possibilities for z, of course. And now the prediction is what you're supposed to do is you're supposed to take 2 of these at random, 2 maximal isotropic subspaces, and intersect them, and look at the dimension of that intersection. And so that's going to be some random variable, and you can look at the distribution of that. And the prediction is that this intersection is supposed to be like the Selmer group. And well, except that we should, I mean, the Selmer group can be arbitrarily large in dimension. So to get the conjecture is actually you take this intersection, the distribution of this in the limit as this n goes to infinity. And we prove that these distributions do converge to a distribution supported on the non-negative integers, and we predict that that's the distribution, that's the actual distribution of the Selmer group, P Selmer group of E, as E ranges over all elliptic curves over Q. Okay, so and there are a lot of reasons to believe that this is correct. So. Well, first it was designed to be compatible with Heath Brown's theorem, and it's also compatible with these. And in the case p equals 2, and also once we realized that this was a model that gave rise to this distribution, we actually tried to look if the intersection of 2 maximal isotropic subgroups is giving what seems to be the distribution of the Selmer group. We thought maybe the P Selmer group actually is an intersection of maximal isotropic subgroups. That would be the most natural explanation for why is, and in fact we've discovered that it is. It is an intersection of 2 maximal isotropic subgroups in a certain infinite dimensional, locally compact FP vector space. There's some sense in which you can work with a random maximal isotropic subspace in an infinite dimensional subspace, with a little bit of care. And so the P Selmer group actually is an intersection of that type. So that's another good reason to believe that it's not just matching distributions. There's actually some arithmetic that makes this look like it should be coming from this kind of model. Moreover, this conjecture is compatible with various theorems that have been proved about the average size of the subgroup. I mean, that's not as much information as the distribution, but you can get, of course, So the first theorem of this type is due to Johan de Jong in 2002 in the function field case, and then later Bhargava and Shankar found the average size of the Selmer groups for small values of n, for n up to 5, and in every case it's compatible. Well, I guess every prime case it's compatible with this prediction. And also this conjecture, so sort of a function field variant of this, but it's kind of a little bit of cheating function field invariant where you let Q go to infinity, of the constant field size go to infinity. But anyway, in that limit, this is actually proved in that function field case, and that's a very recent result. Okay, so that's the model for the P Selmer group. But as I said, going back to the previous slide, we really want not just the P Selmer group, but we want the P to the N Selmer group and take the direct limit. And so we really want a model for that as well. And so after Eric Rains and I came up with this, we discussed this with more people. So this is Bhargava, Kane, Lenstra, me, and Eric Rains, and together we generalized our prediction, our linear algebra model, to get a prediction for the P to the E Selmer group for every power of P, and then by taking a direct limit, we got a prediction for the whole P to infinity Selmer group, and then in fact we made a prediction for the whole sequence, as considering the whole sequence as a random, or as some sort of a random variable taking values in exact sequences of ZP modules. And once we have this also gave predictions for what the distribution of this should look like, of the P primary part of the Tate-Schafer average group. And this distribution, this prediction was expressed in terms of, it said basically that this should behave like a co-kernel of a random matrix, and the random matrix should be sampled from alternating matrices. So these are matrices antisymmetric, antisymmetric matrices with entries in ZP. And so you view this such a matrix as a map from ZP to the N to ZP to the N, and then you take the co-kernel, which usually, which it might not be finite, but you take the torsion submodule of that, which is going to be some finite abelian P group, and that's what's predicted to model this P primary part of this Schafer average group. And in particular, you can show that this co-kernel, the order of this is always a square, which matches what people predict that should happen here. The Tate-Schafer average group should also always have square order. But one thing that happens with this group is that there's actually a different distribution of this group for each value of the rank, for each possible value of the rank of the liptic. And this is analogous to what happens in the Cohen-Lenstra heuristics for the statistics of class groups. In that case, the distribution of class groups, it depends on the unit rank of your number field. So for example, there's one Cohen-Lenstra heuristic for imaginary quadratic field, and there's a different heuristic for real quadratic fields. And so the same thing happens here. We predict that the distribution of this should be very different for different values of rank. And for example, for rank 0, this tends to be large, kind of like the class groups of imaginary quadratic fields. And then for ranks higher, 1 or higher, this tends to be quite small, as happens with class groups conjecturally for class groups of real quadratic fields. Okay. And the way that you get this different distributions is by conditioning. You don't just take any random matrix in here with respect to Haar measure. You sample it from the subvariety consisting of matrices whose kernel has rank R. And again, there are reasons to believe this. It's compatible with other conjectures that have been made, and also this is if you, instead of looking at E varying over all elliptic curves, if you only vary E in a family of quadratic twists of one elliptic curve, then this is actually this conjectural distribution for the Selmer group has actually been proved by Alex Smith a few years ago. The plus means this. I think it's not yet published, but he keeps modifying it and making it better. Okay. Anyway. Okay. So now what I want you to focus here focus on here is the fact that the model for this, for rank R elliptic curves, is obtained by conditioning on this condition. And because of that, it's natural to think that the rank of this kernel should be the thing that should act like the rank of the elliptic curve. And so now what we want to do is turn things around and ask, okay, now just suppose you take a random A, what is the distribution of this rank as you sample A from this group? I mean, this is actually yeah. So I mean, the answer is usually going to be 0 or 1, 50% each. But that's because we're using ZP coefficients for these matrices. If instead you use using ZP coefficients, in which case your lower dimensional subvarieties will occur with R measure 0. If instead of using ZP coefficients, you use Z coefficients, and you also impose a bound on the size of those integers, then you'll have some small but final probability of this being more than just 0 or 1. And so that's what the final model is going to be for predicting, for trying to figure out what's happening with ranks. Yeah, because otherwise, because as it stands, this would just say that, yeah, if you view n as being random, all this would say is that 50% of the elliptic curves are going to have rank 0 and 50% have rank 1, but it doesn't tell you anything about what's happening with the 0% that have higher rank. Okay, so here's the actual final model for how you're supposed to model a curve, and the model is going to depend on the height of this elliptic curve, and the height is going to dictate what the integer size what the size of the integers in this matrix are. And the bigger h is, the bigger the entries will be, and if the entries of this integer matrix are larger, then for things like, well, the determinant is less likely to be 0 then, because the determinant is a priori a big integer. And so, yeah, so we're going to have these. So in terms of h, we're going to have some growing functions tending to infinity. And then what you do is you choose an n. So this is going to be the n for the n by n matrix. And you choose a random parity because we expect that elliptic curves have random parity of rank. And you choose n to be of size about this. So that's also, n is also going to be large, depending on the height of the elliptic curve. And then you choose a random matrix with integer coefficients, alternating matrix, and with all the entries of absolute value bounded by this other large function. So I'm going to have to tell you what these functions are later. So that's part of the parameters of the model. And now in terms of those, so now you have this random matrix. So let's call it A. And then you take the co-kernel and the torsion subgroup of the co-kernel. That's supposed to be the model for the Tate-Schaff-Rayburn group. And then you take the kernel, which is some ZP submodule. Z module now, because we're doing Z matrices, integer matrices. And the rank of that kernel is supposed to be the model for the rank. So I'm going to call this the pseudo Tate-Schaff-Rayburn group and the pseudo rank of the elliptic curve. Yeah. Okay, now I haven't quite specified everything because the model, to completely specify it, I have to tell you what these functions are. And it turns out that the only thing that really matters is this combination of the functions, x raised to the eta. And the model is going to be specified by insisting that this grow at this rate with h to the 1/12 plus O1. Now, the reason for choosing that, where does this 1/12 come from? It comes from, this is sort of a calibration that comes from what we know about the arithmetic of elliptic curves. We know something about how large Tate-Schaff-Rayburn groups are on average, statistically. For example, if you vary E over all rank 0 curves, then if you assume standard conjectures, you can actually work out using a little bit of analytic number theory what the average size of the Tate-Chapman group is. And so our model better be such that the average size of this pseudo Tate-Chapman group should have the same asymptotic growth. And that's exactly where this formula comes from. So this constant is set to just to make that work. Okay, but now, and now once you have this model, you can ask what are the consequences of this? Because now they have these things which are just defined by pure linear algebra. There's no arithmetic, there's no elliptic curves, well, except for this number, the height. The elliptic curve itself does not really play any role in the definition of these quantities. And so we can actually, without doing anything hard, we can prove theorems about these numbers and pretend, so we can prove theorems about the model, and then the hard conjecture is that the theorems about these things are actually going to be true for the actual Tate-Chapman group and the actual rank. So okay, so here's the main theorem that we proved about our model. So once you have the model, you can predict how many elliptic curves of height up to h have pseudo rank greater than each integer. It's like, okay, so we know that most elliptic curves are supposed to have rank 0 and 1. So you can ask how many elliptic curves have pseudo rank at least 2. And that turns out to be a lower rate of growth. So this is the h to the 5/6 that I had on an early slide. These are essentially all, these two together are all elliptic curves. So 50% of each. And the rest is all 0%, but now we can see how big that 0% is. So this is, as h goes to infinity, it's 0%, but now we can quantify it. And what comes out of the model just by proving this theorem of linear algebra is that it's less than this number by h to the 1/24. And each time you ask for pseudo rank being 1 larger, the fraction of elliptic curves that satisfy that condition drops by another h to the 1/24. And so, well, you can see where it's going. So once you get up to 20, well, okay, so actually, so I mean, there's no difference between 0 and 1, but this is what the theorem, we actually proved this, and this, so and then but once you get up to 20, it's h to the 1/24. Then once you get up to 21, it's h to the 0, except, well, it's hard to say which way the 0 goes, because our heuristic is not precise enough to predict. I mean, there might be log factors, log h or something, and we don't know. But anyway, but beyond that, the next one would be h to negative power. So we expect that if the expected number of elliptic curves of pseudo rank greater than 21. I mean, you can calculate this just by then this turns out with probability 1. This is finite, and so okay. Of course, I mean, the only problem is this, again, it's the pseudo rank, not the actual rank. But I mean, if the model is really accurately predicting what's happening, then it's reasonable to say then this should be true for the actual ranks as well. And you can ask, how does this compare with reality, with what we actually know about elliptic curves? So Noam Elke's, the records for elliptic curves that are currently known are that, well, if you want to have a family of infinitely many elliptic curves of rank at least some number, it's known that there are infinitely many of rank at least 19. And there are also some isolated examples that Noam Elke's found of even higher rank, and the largest rank found was 28. So, but this is all consistent with our predictions so far, at least. And as I said, even if somebody finds a family, an infinite family of rank 22 elliptic curves, I mean, I would say, okay, it's probably still okay. But obviously then I would still believe that the ranks are uniformly bounded, but because as I said, this model is not. It's quite possible that there's some special families where there's more going on than this model predicts. But I think but things would have to go very wrong in order for the ranks to be unbounded, at least. So okay, so all right. Now another thing you can do is you can, instead of looking at all elliptic curves, you can sort of filter the heuristics according to the size of the torsion subgroup. So here on the left, I have all the possibilities for the torsion subgroup of an elliptic curve according to Mazur. And you can if you fix a certain torsion subgroup, like you say, oh, I'm going to only look at elliptic curves with torsion subgroup Z mod 3Z. Well, then they're no longer h to the 5/6 of those. It's much rarer to have an elliptic curve with that torsion subgroup. They're only h to the 1/3 elliptic curves of height up to h. And because of that slower rate of growth, you have fewer chances to get high rank. And so if you do the same calculation, then the heuristic, you can prove that at least you can prove something about the pseudo ranks. And in that case, you don't expect to get rank up to 21, infinitely many of rank up to 20 or 21 anymore. You expect a bound of 9 instead. And so you can calculate this. I mean, we calculate this number for every possible torsion subgroup, and this is what our model predicts. And you have a whole table of things you can compare with reality, with what is actually known. And so this is the upper bound for the rank of elliptic curve with this torsion subgroup. I mean, excluding finally many exceptions. So that's the number beyond which you expect finally many. And this last column is showing what's actually known. Each entry in this table is representing an actual family, is the largest rank that has been observed for an infinite family of elliptic curves. So I already talked about the 19, but if you look at elliptic curves with torsion subgroup Z mod 3Z, there is a known family, an infinite family of elliptic curves with rank at least 7. And and in every case so far, the proved every known example has been compatible with our heuristic. Now, I should say that there are two cases here, the ones with the star, where it's probably true that they're infinitely, where this 3 is probably a 4. Because it's a family where it's an infinite family where it's known to have all the elliptic curves have ranked at least 3, but it's probably true that the sign of the functional equation forces the elliptic curve to have rank 4 about half of the time. This is okay. Anyway, this is some work of this is some work that was done recently, finding so it's Andre Duyela and also Matia Kazalitsky and Juan Carlos Peral. But as I said, even though this may be the case, I still think I would say that's a special family. So it doesn't make me want to throw away the whole model. There's too much else that makes sense. And you can see also that it's somehow that there seems to be something correct about the model, and that these numbers are actually, they're surprisingly close. I mean, in fact, most of these known examples were found before we even came up with our model. All right. So let me now. So to summarize all this, so our heuristics. What we did is we started with heuristics for Selmer groups, and that led to a model for a complete package of predictions that simultaneously predict what the behavior of ranks, Selmer groups, and Shafarevich-Tate groups. And many aspects of this model are supported by theorems that are compatible. And so far, all these theorems have been compatible with our model. And yeah, and in the model, the pseudo-ranks of all but finally many elliptic curves are bound by 21. So we take that as evidence that the same thing should be true for the actual ranks. And in particular, well, even if it's not 21, I feel quite strongly that it seems quite likely that the rank should be uniformly bounded by some number. I would guess if it's not 21, I would guess it's not too much more than 21. So, all right. Now there are various ways you can try to extend these heuristics. You can ask what happens if you replace Q by higher number fields, or if you replace, or you can also ask what happens with higher dimensional abelian varieties. And so maybe I'll say a little bit about those. So yeah, so let me first talk about yeah. So I've about 18, 19 minutes, right? Is that correct?
Right.
Yes. Okay. Good. All right. So let's talk about other number fields and global fields. So either a finite extension of Q or the function field of a curve over a finite field. So let's take that to be K. And we can try to do the same thing. We can take representatives for the isomorphism classes and try to take and define this lim sup of the ranks. So this is the number such that this is the highest integer such that there are only finally many elliptic curves of rank greater than that. So our heuristic predicts that this for the rational numbers for Q, this number should be 20 or 21. It's uncertain because of that little O1 in the exponent. And we went through our heuristic and did it for a number field as well. And for every global field, in fact, it gives the same prediction that it should be 20 or 21. And you can ask, okay, how does that match reality? What will you actually know about ranks of elliptic curves over number fields and global fields? And actually, it doesn't work so well. So first of all, for function fields, it was already known. Tate and Shafarevich proved that the ranks are unbounded, and those are super singular examples. But Ulmer gave other examples later that were of ordinary curves as well. I mean, on the other, yeah. So and even for number fields, there's a BK we in our paper with Jennifer Park and John Voight and Melanie Matchett Wood, we actually proved that there are number fields for which this lim sup this lim sup can be arbitrarily large. There are some special number fields where we can prove. So for example, we can find a number field over which we can prove that there are infinitely many elliptic curves of rank greater than 1 million. And so we found two ways of constructing such number fields that have infinitely many elliptic curves of rank greater than 1 million, and you can find such number fields in anti-cyclotomic towers of imaginary quadratic fields, and you can also get this kind of bound by taking multi-quadratic extensions of Q. So you just take Q and you adjoin a lot of square roots. And so yeah, okay, so this seems very bad from given that the heuristic is saying that this B sub K, this lim sup of the rank should be 20 or 21. So the way we reconcile these is we make the observation that the elliptic curves that are of high rank in both over number fields and function fields, the only way known to make elliptic curves of high rank are to take elliptic curves that are actually coming from a lower field. So if you exclude the elliptic curves that are instead of just being defined over K, they're actually, if you exclude the ones that are actually base extensions, base changes from elliptic curves from a smaller field, then you define a new set, a restricted subset, And then you can ask the same question: what's the lim sup for those elliptic curves, the ones that are really defined over K? And then it's possible that you again have uniform boundedness. And I mean, the bound is not necessarily going to be 21 over here anymore, because there's an example of Shiota of a rank 68 curve over C adjoint T, and it's actually defined over Q bar adjoint. I mean, yeah. So this example, it's actually defined over K adjoint T for some number field you can get. And so by specializing then this T, you can get lots of elliptic curves. I mean, they'll all be elliptic curves of rank of J invariant 0. But anyway, you can find examples of things of elliptic curves that are not isomorphic over K, and infinitely many will rank at least 68. So, okay, but still, it's still conceivable that it's uniformly bounded for every global field K once you exclude these lower ones from lower fields. Okay, so now let me say, okay, so that was for higher number fields and global fields, but now let me change directions and ask what happens if you replace elliptic curves by abelian varieties of higher dimension. So in this case, so the question is, do you still have uniform boundedness? So I mean, you have to fix the dimension, of course, because otherwise you could just take an elliptic curve and take a big power of it, and the rank you take e to the 100 anyway. So so the best you can hope for is a bound that depends on the dimension of the abelian variety, and it's also going to, of course, need to depend on the number field, because I mean, even if you have an elliptic curve, you can make the rank large by just adjoining the coordinates of a lot of points. And so, okay, so you can ask this question: is there a uniform bound where the bound depends only on the dimension and the degree of the number field? Now, you can do some certain reductions. You can, by doing restriction of scalars, you can replace your number field by Q at the expense of making the dimension larger. So let's do that. So we might as well, for the sake of this question, might as well assume that K is Q. And moreover, the abelian variety, you can replace A by A to the 4th cross A dual to the 4th, which according to Zarhin is always principally polarized. And that just multiplies the rank by 8. So you might as well assume that by doing that, you can assume that your abelian varieties are all principally polarized. And the advantage of doing that is that for principally polarized abelian varieties of a fixed dimension, there's a moduli space. And you can actually find a single algebraic family that even covers all the isomorphism classes over Q. And so now we're just asking about one big family parameterized by one variety that includes all the isomorphism classes of all the principally polarized abelian varieties of dimension G over Q. And for that family, you can define some kind of naive height just in terms of the coefficients of the equations that define the abelian variety. And well, then if you ask how many abelian varieties have height up to h, so I mean, it's not going to be h to the 5/6 anymore, but it will still be h raised to some polynomial, because you only have finitely many. There are only finitely many there are only finitely many coefficients in these equations, a bounded number of coefficients in the defining equations. So okay, so it's not h to the 5/6, but it's h to some power. That's going to be the upper bound for the rate of growth. And so now, if you believe that as for elliptic curves, there is some there's some pseudo rank that gives you a pseudo rank such that the probability behaves analogously to the way that you would expect based on what happened with elliptic curves. If the probability, every time you ask for rank 1 higher, the probability of having pseudo rank beyond that goes down by some fractional power of h to the 1/24 or whatever. Well, then eventually, because it started out as h to the some constant here, if you keep dividing by h to the 1/24, eventually it'll go below, the x1 will go below 0 again. And again, then the model will predict that you'll have the pseudo ranks will be bounded with probability 1. And so then okay, so there are a lot of ifs here. So I mean, this is maybe not as convincing as as the elliptic curve case, but I don't know, but I think I think it's reasonable that this could be what's happening. And so based on this, I would guess that the answer is still yes, that there just aren't enough abelian varieties for them to find examples of very large rank. So I would guess that again, that the answer to this question is yes. Okay, so now in the final minutes of my talk, let me say how you can use this combined with some recent theorems to say something about higher genus curves. So let's talk about curves of genus greater than 1 over a number field. So in that case, there's the Mordell conjecture, which is not a conjecture anymore since it was proved by Faltings, and Voight gave another proof, saying that in that case, for a curve of genus 2 or more, the set of rational points is finite. And that's true over any number field. And recently, there's been a proof of a uniform version of this conjecture. So uniform in the following sense. So look, this is work of Dimitrov, Gao, and Habegger, based on taking Voigt's proof and proving, and then combining it with some kind of uniform version of the Bogomolov conjecture. And so for this, what they do is they give a bound on the number of rational points as x varies, and the bound depends only on the genus of the curve, the degree of the number field, and the rank of the group of rational points of the Jacobian. And so, yeah, so there's this constant that just depends on, and they also tell you what kind of dependence on the rank it is. It's just exponential on the rank, and this is just some constant depending on genus and the degree of the degree of the number field. And recently, Lars Kuhne also eliminated the dependence on the degree, so you can actually replace this by just constant depending only on the genus, and raise this. And that, I mean, the number field in some sense still comes into it because, well, it comes into it through the rank. Oh, sorry, this should have been K here. That's okay. Let me write. That's a rank of K. Yeah. Okay. So, okay. So and Qinyi Yuan gave a different proof of this uniform Mordell conjecture based on the theory that he worked out with Shou Zhang, the theory of adelic line bundles. So okay, now, but what I want to say, based on if I take this theorem, and now I combine it, but now I look at this bound, but now if you believe what I was telling you on the previous slide, that what I was telling you on the previous slide is that this rank of this abelian variety should be uniformly bounded, depending only on the dimension and the degree of the number field. And so that means that if you plug that heuristic into this theorem, then they would tell you that you can, this thing just depends on the genus and the degree. So everything now, this whole thing now just depends on the genus and the degree. So it predicts, and so you would get, if that heuristic on the previous slide is true, it would imply that the number of rational points can be bounded just in terms of the genus and the degree of the number field. And this is a conjecture that was made by Caporazzo, Harris, and Mazur back in 1997. And well, okay, I guess the way they stated the conjecture originally was it was a bound that depended on the genus and the number field. And the fact, and then Abramovich gave some evidence that you could actually make it that you could also vary the number field over the number field of fixed degree. He actually did this after this, but I guess sometimes things don't get published in the same order that they're done. So, yeah. Okay, so yeah, so personally, I believe there's a good chance that all these things that I've said in the talk are true, that the ranks of abelian varieties are uniformly bound in this way, and also that the number of rational points in higher genus curves is uniformly bounded just in terms of the genus and degree. I mean, it does have to depend on these two things. Otherwise, I mean, yeah. So, but yeah, okay. So I'd like to end here. So yeah, thank you very much for your attention. I'd be happy to hear any questions.
Any questions?
At the beginning of your talk, you said that certain estimate conjectures are proven for t equal to 2. Characteristic 2 is usually the odd one out, the choice of term. What is particular in the case of t equal to 2?
So it's a little bit hard to hear. So it was something about what was equal to 2, the genus.
So in the beginning of your talk, you mentioned that some conjectures were proven in the case in characteristic 2.
I think, yeah, okay. So let's see. I think maybe you were talking about this slide, perhaps.
Exactly, yes.
Yeah.
So is that related to the fact that you're choosing a quadratic form, or how is that? Why?
So this, I think, so the Heath-Brown's result, for example, for p equals 2. I mean, I think it's just that it's just easier to analyze the two-Selmer group than it is to analyze the p-Selmer group, just because to understand it, you need to know the Galois action, the action of the Galois group of Q bar over Q acting on the p torsion points. But for p equals 2, you can just see what the two torsion points are. You know that they're just, well, if your curve is y squared equals x plus x with b, you know that the two torsion points are just the points where the y coordinate is 0, and so you can just see directly. And in fact, he was doing even something more special than that. He was actually looking at a case where all the two torsion points were rational. So he was actually looking at a family of curves where there was just y squared equals a cubic polynomial that factors completely over q. And in that case, it's much easier to analyze to figure out what the two-Selmer group is doing. And over q, you can't even have all the three torsion points, say, defined over q, because the Weil pairing would then tell you that you would have a cube root of unity inside q. And so the only case where you can do this it's just a matter of, I mean, it was hard enough what Heath-Brown did for p equals 2 that I mean, nobody, there hasn't, So, so that's the only case we had to in order to figure out what we expected the distribution. But actually, it's very useful. We were actually quite happy that p equals 2 was the case that they did, because at first, actually, before we came up with this model, at first, instead of taking a maximal isotropic subspaces for a quadratic form, we did quadratic maximal isotropic subspaces for a symmetric bilinear form, which is not quite the same thing as a quadratic form in characteristic 2. And we found out that our answer, that we were getting the predictions we're getting seemed to be not quite right when p equals 2. And so this is what actually gave us the clue that we should be looking at quadratic forms instead of symmetric bilinear forms. So anyway, it's a very good question. So.
Thank you. Any other questions? If no other questions, let's thank our speaker again. Thank you. Thank you very much.
Thank you very much, and I hope you enjoy the rest of your conference.
Thank you.
I wish I could be there.
Maybe sometime in the future.
Okay. Okay, and thank you all for managing the logistics. I know it's sometimes not easy arranging these Zoom talks. So.
for sure.
Okay, goodbye.
Take care now.
Recording stopped.